Okay, I have recorded this. If I want to see these things, cars that ahead, so I have speed and distance, something like that. So by using speed and distance, I want to construct this type of curve. So if I want to write in here like this, and then I want to put here speed, and I want to put here distance, something like this. So speed is going like this way. And for distance is like something like this. And for this, we want to construct a curve like this way. Okay. So how can I do these things? Take a look at this one. If you want to use the local polynomial non-parametric regressions, then your responsibility is to run all up until here to there. Okay. So you run here control R, it is run. Okay. Now I want to, this is the local polynomial one, and then come in here. This is the local polynomial in here. Cars is the data. LP as boot is the functions that I have created. LP as boot is the function that I created in here. LP as boot. LP as boot extends all the way from here up until there. All of this LPS boot. So when after running these things, now I want to run this part. In this part, cards is the data. LPS boot is the code for the local polynomial regressions that I already ran. This is, I take speed as a independent variable and distance as a dependent variable. I am replicating it 5,000 times. Okay. And then with cards, this is the plot, speed, distance, less means it is like a raw point size. And this is the title of the graph. And this is with M, this is the M. I want to do mat plots in here. So that means matrix plot. Mat plots means matrix plot in here, X and all the three, Y as well as your lower upper limit, upper limit. And then this is the color and these things. So if I run these things, and then you will see a graph. This is the graph has been created, speed and distributions. So if I want to change LAS equal to suppose 3, then see how the graph looks like. It's no changes in here. So if I want to put here 10, let me see whether it will be. Oh, 10 is not taking. So let me put here 5. 5 is not taking. So less is taking 1. So exactly I cannot recall these things, what does less stands for, but I can explain it to you later what is S. So this is red line is bootstrap, pointwise bootstrap confidence band, and dots are the, for example, these dots stands for speed is in here and distance is in there. So this is the dot. And this dot stands for speed is in here and distance is in there. Okay. So by using this dot, we want to fit a smooth line in a smooth curve. So that curve is obtained by the local polynomial regression. So now in your case, now I want to focus these things in your case. Okay. Before focusing these things, this is called the local polynomial. Now, next one, if you take, it is said as a kernel. Okay. So you can use either local polynomial or kernel. This is the kernel one. After running the kernel one, I have to come down in here. This is for the kernel. If I want to run these things, then this is the curve I will get for the kernel. Similarly, if I want to do it for the spline, this is what I have to do. 3 non-parametric regressions. You can use one of the 3. Okay. So this is the spline one. And then if you can come in here, this is the spline one. This is the spline one that you have seen. Okay. This is the spline one. But if you want to take a look at the all 3 together, then you have to run all of these things. All of these things, then this is what you will see. Okay, here is the graph, all 3. You can use any of these 3, but in what of your setting? Your setting is this. Your setting is this. You have a you have a data. On that data, you put here respondent is. Respondent age. You put here respondent age. Okay. Suppose respondent age, you started here 20 and 21, 22, up until suppose you stop in here 70. Okay. So in age 20, suppose there are how many age 20? Suppose age 20, there are 100%. Suppose 1000 person at age 20. At age 20, 1000 persons, and you found 30 of them has a high blood pressure. Okay. 30 of them have a high blood pressure. 30 divided by 1000 is what? Is the proportion. This is equal to proportion at age 20. Okay. Similarly, at age 21, you will get suppose 500 people, and you get like 21 of them has a hypertension. So this is a proportion of hypertension as age 21. Similarly, you will come in here, you will get at age 70, you will get suppose 1200 persons, and the 1200 persons, the you have found suppose 190 as a hypertension. So then you can put here P 70. So these are the proportion will be put it in here. This is the proportion. Okay. And at age 20, you got a proportion in here. You got a proportion in there. You got a proportion in there. You got a proportion in there. Proportion of hypertension you got like this way. Okay. So, and then you will construct a curve for this one. Okay. So this curve you constructed one for the suppose this is the entire curve for entire populations. Now you have to do the sub analysis, or subgroup analysis. Subgroup analysis. You can do now subgroup analysis. So this is the curve for the rural. Okay. And then you can get another curve for the urban. Okay. From this curve, we can say that, well, proportion of hypertension, um, onset of proportion or hypertension is higher for the urban people compared to the rural people. Or, or you can construct like this. You can construct like this. So you can construct another one like this. Okay. And then you can say that this is for the people with no education, no educations. Okay. This one is the curve people with the primary educations. This one of the curve with the people with higher educations. Then you can see that you can tell that higher education people has a higher hypertension proportion compared to the other. This is done by the age. So you have to split your data. You remember you have a data. Suppose your data is D1. D1 is your data. Now you have to create a D2 data with D1, split D1 by respondent current age, RCA. Okay. Then you will get a data. And D2 1 is the first data corresponding to age. Suppose I don't know what is the minimum age. Suppose 20, and then D 2 is the data corresponding to age 21. Suppose it has a 500 rows and 21 columns. This one could have a 700 rows and 31 columns. It will continue like this. Okay. So the reason I said these things, now for these data, you already created a hypertension variable. From there, you can compute a proportion for this by running single loop. Okay. By running single loop, you can compute this thing. For now 20 to 70, there are 50 A's. 50 A's, you will get 50 data. Each data is of different length. From that data, you have to compute the proportion of hypertension, and you can construct this curve based on criteria. So for example, you can definitely do one curve, one for the type of place of residence, type of place of residence, So that means in this graph, you will get graph A for the rural and B for the urban. Okay. So that means you will get one curve like this. Here is the respondent current age. Here is the proportion of hypertension. Then you can get one curve. This is for the urban. And you can say that this is for the rural. Okay. This is one graph. Second graph you can get by wealth index. Okay. In wealth index, here is the respondent current age. And there you will get the curve. One curve you got like this. This is for the poor people. Then this is for the middle people. And that is for the higher people. Like higher rich people, medium income, and poor people. You can get like this. So you can get here three curves. Okay, you can get three. Then from there we can say that, well, people with rich social status have a higher hypertension curve compared to the poor people. So number three, similarly, you can go for the education type. Okay, education type. And then you can number four you can do for the for the working status. Okay, working status, and if you have a very strong religion variable, you can construct five like this. Okay. So so far what you have done these things: summary statistics table, summary statistics table. This is what you have done. You did bivariate analysis by using chi-square bivariate analysis. And then number three, you have done multivariate logistic regression, I guess. Multivariate logistic. And then multivariate logistic you have used here, like 1 equal to hypertension, 0 equal to no hypertensions. And number four, you got quantile regression. Quantile regression. Quantile regressions only used by the people who are using with the blood pressure data, but the person who is using STI, he is using just the multivariate logistic regression. Okay. And then number five today that we have learned is called the smoothing curve. Smoothing curves. Okay. And number six, which I will discuss after the spring break, is called the random forest with LOCO. Random forest with LOCO, which I am going to discuss in next 15 minutes. Okay. But I will discuss more again in next on after the, I think 18. After 18, I will discuss more. Now let me discuss little bit what is random forest with LOTO. So I'm next 15 minutes I'm going to discuss random forest with LOCO, and then our all analysis will be done. Random forest with LOCO. This is what I am to do. Okay. So try to understand what a beautiful thing is this. Suppose you just have three variable yi equal to beta 0 plus beta 1 x1i, beta 2 x2i plus beta 3 x3i plus epsilon I. So this is, and suppose this is your logistic regression, LR logistic regression. So take a look what I am doing, and this is called the full model, and this is called the reduced model. Beta 0, beta 1 x1i, beta 2 x2i, and epsilon I. Okay, this is called the reduced model. Okay, full model and reduced model. We are using logistic regression. What I'm doing, suppose this is our data. Okay, this is my y, this is my x1, this is my x2, this is my x3, and this is my row 1, 2, 3, 4 up to 5,000 row. What I will do, I will take a, from this 5,000, I will take a sample of size, suppose 2,000. With this 2,000, what I am going to do, I will feed the full model. From full model, I have estimated what? Betas. 0, beta 1, beta 2, beta 2, beta 3. All of these things I have estimated. Okay. I have estimated these things full model, and my estimated model is this. Y I hat equal to beta 0 equal to 1, beta 2 equal to 2x1, and beta 3 equal to beta 2 equal to 3 x2 suppose, and then beta 4 beta 3 beta 0 beta 1 beta 2 beta 3, this is beta 4 x3, suppose this is what. So now I took any x1 x2 and x3 from this, any x1 x2. Suppose I want to take x1 equal to 2, x3 equal to 3, and x4 equal to 4. This x2 x3 x4 value is coming from this data, and then I plug it in there. After plugging it in there, suppose I got the value of suppose 120. Okay, now I want to the sample that I use, this sample. Okay, this sample, this same sample, I want to feed the reduced model. The same sample, I feed the reduced model, and I had now beta 0, beta 1, and beta 2. Okay, so now this is the same sample, reduced model I feed. After feeding the reduced model, same sample, I want to find these things, y I had. Suppose this is equal to, again, this is equal to 1.5 and 2.5 x1, and then 3.5 x2. Okay, now suppose here I got the value, I got the value here is suppose 119 I got here. Okay, so now this is coming from the full model, and that is coming from the partial model. So I take a absolute difference, full minus partial model. Okay, and then I got a difference of 1. Okay, so this is the predictive uh, difference, like the how much predictive error you are making when you are dropping one variable. Loco means leave one covariate, out. That is the meaning of the loco. Okay, so what I did, I leave one covariate out. With the same sample, I fitted reduced model, and for a specific x1 and x2, 2 and 3 I plug, I got this value. So the sample that I pick, like a sample of size 1 for x1, x2, x3 from this data, and use the predictive value for the full model and reduced model, and I take the difference between them, and I got the 1. Okay, so this is the predicted difference. I got a sample of size 2000. I have to repeat these things again for another sample of size 2500 from a total sample of 5000. I have to repeat it again for the sample of size 3500. I have to repeat it again up until I can repeat it, suppose 200 times, and then 200 times difference between partial and full model, and I will get 200 partial, and this is the first partial and full model predictive difference for a specific sample. This will be the second full and partial model difference between the full and partial. And this is the third. It will continue like this way. Okay, it will continue. And after doing this continuation, you will find the average, how much error you are making on an average. Okay, 200 predictive difference you are getting, and 200 averages you will find. And then you can say that, well, when we uh, when we drop or leave x3, we got on an average that much predictive error. This thing will continue again for variable x2 and variable x1 each time you will. And then if you drop one by one variable, you will find something like this. You have to construct like this. Okay, so this is the, if x1 is left, then predictive error you will get like this. Okay, this is the height. If x2 is left, then you will get predictive error like this. If x3 is left, you will get predictive error like this. Then you said, well, x3 is the least important variable, whereas x1 is the most important variable for the model. If we ignore or leave x1, we will lose more predictive power. Okay, that's the way you will have to compute these things. So after doing these things, then our analysis is done. Rest of the 6 weeks or 7 weeks, we will just write the paper and finish these things. Do you understand what I said?
Yes. Yes, Professor.
Okay,
I have a
so
question.
these things, yeah, listen, the code and everything is in online. You will find, sounds like it is difficult, but it is not difficult. But if you want to write this from the scratch, then it is difficult. But packages are in there. Our package, Python packages are in there. You can use them. Okay, someone wants to ask me question. What is the question?
Yeah, so in this graph you drew x1, x2, and x3. Is this so x1 is the variable that's left out?
Yes, when axon left out, how much predictive error are taking, how much predictive error you are making by taking the difference between full model and partial model. But remember, you have to do this at least 200 times, okay, on an average, so that each time from a sample of size 5000, you are taking a sample of size 2000, 2500, 2300, 1700, 3700. You are taking sample and again, and each time you feed the full model and partial model. And for x1, for a particular x1, x2, x3, you compute the full model predictive value and partial model predictive value, and based on that you will compute the like what is called absolute error difference between full model and partial model. And you have to average all the 200 predictive errors, so that on an average we can say. So here we are saying that on an average this error would be made. And why I said that random forest? Random forest means this is your data, and you are taking a sample, and you are making a decision tree. What is the decision tree? Decision tree you are making, you are making full model and Partial model. And full model and Partial model, you are taking the difference and you are making one difference in here. Like, so this is the decision of predictive error. And then you are making another sample, another decisions you are making. This is the predictive error between full model and Partial model. So the random forest main idea is taking a sample, fitting the data again and again, and each time making a predictions whether the prediction is following a particular value, like whether greater than 0.5 or less than 0.5. If greater than 0.5, it is more close to 1. That means yes. And if it is less than 0.5, then it is close to no, that means not. Similar idea I copied from the random forest and applied in here. This random LOCO and random forest was developed in 2017 by a professor at Carnegie Mellon. So we are going to use these modern methods in our paper. So with the multiple logistic regression, quantile regressions, and then random forest with LOCO and kernel and local polynomial or spline smoothing curve, the paper will have lot of multivariate analysis and bivariate analysis and non-parametric and parametric regression model, and we will have a higher chance of the paper being accepted to a good journal. Any other question?
I have
No.
Latifa, you have any question?
Yes. So for the local and random forest, should our dependent variable be demi-variable or continuous one?
So
Hypertension.
you are doing what? You are doing hypertension, right? 0 and 1, right?
Yes.
Okay. So if 0 and 1, so that means it will be your logistic regression. Here it will be your logistic regression.
Okay, okay. Because I have done quantile also, so I used for the quantile I have used SBP, the continuous one.
Yeah, now that is, but we are doing these things for logistic regression. Okay.
Oh, thank
See, for logistic regressions, when you are making predictions, you are making prediction between 0 and 1, right?
Yes, on dummy.
So you are making for logistic regressions, when you are these things, you take the sample and full model and reduced model. So full model, you make a prediction of 0.91, and Partial model, you make a prediction of 0.81, right? So you take the first sample. So you are taking 0.91 minus 0.81. So this is your absolute difference 0.10. For the second sample that you take full model and reduced model, after fitting those things for the same data, and then same x values you are plugging there, you got here 0.61, you got here 0.41. You take the difference between them, then this is your difference, right? So you are not going to use quantile regression, you have to use here your logistic regression. And in that way, first, second, third, up to you, it will continue up to 200 times, and 200 difference of this, and all of this 200 difference you will divide it by 200, and then it will be your average predictive error. So when you drop one variable between full model and Partial model, you will continue these things by dropping other variable x2 and x3, and then you construct the graph like this way. So from that way, this is the predictive error. So this is the highest predictive error. So this variable is very important, but the variable x3 is second most important. Variable x2 is the least most important for the three variable model. Okay. Any other question?
No.
So then the class will be short. I'm going to stop in here. You are getting a 1 week full break of Thanksgiving. Okay. Sorry, not Thanksgiving, it's spring break. So we are seeing 18th of March. During that time, I ask you to finish all of this non-parametric smoothing curve as well as random forest with LOCO, and put all the graphs and everything on the class on 18th of March, and I will check each of your works, and then from there will, and by this time, if you have a question, you can reach out to me. I'm giving you a guarantee that the materials that we have discussed, and if all of this material could be put in the paper, I am almost sure the paper will end up in a very good journal. This is number one. And number two, you put all of these things, and if you have any question, you can email me. I am also telling you the random forest with LOCO algorithm looks difficult, but if you can write the algorithm by your own intellect, your programming skill will become very, 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 very high. Okay. But if you do not know how to do all of this coding, there is a packages, you can use those things. Those packages is known as the feature importance package, how to do the feature importance from different types of predictive models. Okay.
Okay. Also, Professor, I want to ask, during the holiday, can we always reach out to you to?
Yes, yes, I'm
Calls?
always here. 9
Okay.
a.m., 3 p.m. and 1 a.m. in the morning. If I in front of the computer, I always respond. Okay.
Okay. Okay. So we can always schedule a meeting in case we have issues. That's what I'm asking.
Yes, and if you schedule a meeting with a group, that will be fantastic too. Okay,
Okay.
I'm going to stop in here. Okay.
Thank you, Professor.
Happy spring break. See you after the spring break. Bye.
Yeah. Thank you. Bye.
Mhm.